In this tutorial, we're going to look at methods for one-sample proportion inference. Before beginning with this tutorial, make sure you've read the health disparities example on the previous page. So let's get started. When we're dealing with one-sample proportions in Stata, there's a few commands that you're going to be using on a regular basis. First, when we're looking at confidence intervals, the CI command and the CII command are the primary commands that are used. CI is used when you have data read into Stata, and remember, when you have this extra I on the end, what that means in Stata is that it's an immediate command, so you don't have to have data read into Stata, you just need the numbers available. When you're looking at hypothesis tests, two commands are used pretty frequently. There's the by test command, and what this is it's an exact test. On the other hand, we have this PR test command, and this is for large sample one proportion tests. So by test is an exact result, and PR test is a large sample result. So let's look at those commands in Stata. Go ahead and open up Stata, and we'll get started with this tutorial. On this web page, you have a link to the CHIS Health Disparities dataset. Go ahead and open up that dataset. Now, we saw in the example that this data set contains a random sample of 500 individuals from California, and you can see we have 7 different variables in this data set. Let's look at the labels. So what we're specifically interested in is this poverty covariate. It's an indicator at 0, 1 for whether an individual is below the federal poverty level. Then we also have this doctor covariate, and that's our outcome of interest. Poverty is our explanatory variable, and then our outcome of interest is visited the doctor in the past 12 months. The first exercise we're going to do is estimate the proportion of California residents who visit the doctor at least once in the previous year. Let's denote this P. So to do that in Stata, we can just tabulate doctor as we've done before. Looking at this table, we see that about 80.4% of the population went to the doctor in the past year in this sample. Now that 80.4% is specific to our population, but we want to make inference about the population of California residents as a whole. So in order to do that, we need to construct a 95% confidence interval for P, the proportion of residents who went to the doctor. And let's do that using several of the different methods that we learned in class this week. To calculate confidence intervals in Stata, you're going to go to the Statistics menu, go Summaries, Tables, and Tests, Summary and Descriptive Statistics, and then click on Confidence Intervals. Alternatively, if you can't remember how to do that, remember you can just type in DBCI. The variable that we're interested in this situation is doctor. Now we need to specify some of the options within this window. The variable type, in this case, we have a binomial variable. And then once I click on binomial, you see that there's all these other options over here for how you want to calculate your binomial confidence interval. There's actually 5 options. We covered only 3 of these options in class this week. If you remember, we covered an exact binomial confidence interval, and then we covered 2 large sample confidence intervals, the Wald test and the Wilson. So in practice, if you have a large sample, the Wilson is going to outperform the Wald. But remember, if you have a small sample, you shouldn't use the large sample procedures. You should really use this exact confidence interval. So let's construct 3 different confidence intervals for doctor. First, we'll start with the exact interval and hit submit. You see I get a confidence interval that's about 76.6% to 83.8%. Now I can construct a Wald confidence interval. And similarly, I can construct a Wilson confidence interval. All right, so I have my exact interval, and then I have my Wald and Wilson interval, which are both large sample confidence intervals. We need to think about, in this example, is it reasonable to use a large sample confidence interval? So to test that assumption, what people usually do, or to make that decision, they take the sample size and multiply by the estimated proportion. So N times P, in our case, that's equal to 98. And we just need it to be greater than 5. So that's okay, but you also need to check that N times 1 minus P is greater than 5. And N times 1 minus P in this case is going to be equal to 402. And so that's greater than 5. So it's okay to use these large sample confidence intervals. Comparing these intervals, we see that this one's about 76.6 to 83.8. This is about 76.9 to 83.9, 76.7 to 83.6. So really, these guys are all almost equivalent. In practice, really you could pick which one you would want to present. The Wald typically performs the worst. So in practice, you would probably want to give either the binomial exact or the Wilson confidence interval. However, this walled interval is actually what you're going to see presented in practice most of the time. And the reason for that is because it is the easiest to calculate. So don't just default to the walled because it's easy or it's because it's what your software program is giving you. Make sure you think through whether or not you might want to use either this Wilson option or the binomial option instead to get better confidence interval coverage. Next, we want to look at these confidence intervals and decide whether there's evidence that at the 95% confidence level, do we think that at least 80% of the population visits the doctor once per year? So looking at these confidence intervals, we see that 80% lies within each of these confidence intervals. So we don't have strong evidence that at least 80% of the population visits the doctor each year. It looks like that proportion is lingering somewhere around 80%. Now let's repeat that analysis, stratifying by poverty level. So what we can do is we can say by sort, poverty, CI, doctor, comma, binomial. Alternatively, if you wanted to do this using the window, you could use the by if in option. We would want to repeat the command by groups, stratify by poverty. All right, let's look at our confidence intervals. For those above the poverty line, we end up with a confidence interval about 78% to 85%. For those below the poverty line, on the other hand, we see a much different looking profile. Note that our sample size is much smaller, so we get a wider confidence interval. And that confidence interval spans from about 57% to about 81%. So this upper bound for the confidence interval is very near 80%, but it looks like we might actually have in the population who's below the poverty line, it looks like the proportion who visits the doctor every year might be less than 80%. We see some evidence of that in our data. So let's conduct a statistical hypothesis test to look at that question. Okay, so what we're going to do now is we're going to define P1 as the proportion of California residents below the federal poverty level who visited the doctor at least once in the past year. Now we're going to test the hypothesis. The null is that P1 is equal to 0.8. And we're going to look at the two-sided alternative that P1 is not equal to 0.8. And we're going to do this at the 0.05 level of significance. First thing we're going to do is we're going to use an exact binomial test. To do this in Stata, you go Statistics, Summaries, Tables, and Tests, Classical Tests of Hypotheses, and then we're going to go to the Binomial Probability Test. You see up here that this is the BiTest command. The variable that we're interested in is the outcome doctor, whether you went to the doctor. And now we're going to say only do this if poverty is equal to 1, which means that you're below the federal poverty level, and hit Submit. Now you see I had a little error there. I forgot to change my proportion. I left it at 0.5, the default. So I really want to test whether P1 is equal to 0.8. So go ahead and change that. You can do that either through the command line or within this window. Change my probability of success to 0.8. All right, and now I can look at my results. Down here, I see my two-sided p-value. Note these first two lines are for the one-sided test. Using the exact binomial test, I find that I have a p-value of 0.057. You can see up here it gives me the sample size, the observed number of successes, the expected, and the proportion under the null, and the observed proportion. So jumping to the p-value, we see that it's 0.057. In this case, we would fail to reject the null hypothesis that P1 is equal to 0.8, but we would note that the p-value is very close to 0.05, suggesting some marginal evidence that P1 might be different from 80%. Next, let's look at a large sample test. For the large sample hypothesis, we end up with exactly the same null and alternative hypothesis, but before conducting the large sample test, we need to make sure that the normal approximation to the binomial distribution is appropriate. So what I would need to check is that N1 times P1 is greater than 5, where I'm defining N1 as the number of individuals in the population who are below the federal poverty level. So in our case, this is going to be 63 times 0.8, and that is equal to 50.4, which is greater than 5. I also need to check that N1 times 1 minus P1 is greater than 5. And so this is going to be 63 times 0.2, which is equal to 12.6. And that is also greater than 5. So I can say, okay, the normal approximation to the binomial is appropriate. Now let's go ahead and conduct our large sample test. To do this in Stata, you go Statistics, Summaries, Tables, and Tests, Classical Tests of Hypotheses, and then now we're going to go down past Binomial Probability Test, and we're going to click on this One Sample Proportion Test. You see this window pops up. The command we're looking at now is PR test. Our variable of interest is doctor, that's our outcome, and our hypothesized proportion is 0.8. Confidence level is 95%. Again, I need to go to this by if in tab and specify that poverty is equal to 1. I hit submit, and I obtain my large sample test. So you see up here the command that was used is PR test. The number of observations is 63. Now let's look at the results of the hypothesis test. First thing we want to look at is what is our test statistic. We see that our test statistic is z is equal to negative 2.01. And we know that under the null hypothesis that z follows a normal 0-1 distribution, a standard normal distribution. Using those pieces of information, we can find that our two-sided p-value is 0.0438. So in this case, we would reject the null hypothesis, and using this large sample test, we would conclude that there's evidence that P1 is less than 0.8. Now, think about this really quickly. Remember, if we go back and we run this exact binomial test, we found a p-value that was greater than 0.05. So we reached different conclusions depending on whether we use the large sample or the exact test. So let's think about this a little closer. We got two different results from the exact and large sample. Now let's say you were writing up these results into a paper. Which results would you present? Take a minute to think about this, because really emphasis on p-values is a very controversial subject among statisticians. I mean, think about it in practice. We got one p-value that's 0.04, one p-value that's 0.06, and really they weren't even that far apart. What if we had something that was 0.049 and 0.051. Convention says we would reject the null for this situation and fail to reject for the other situation. But in practice, there's no meaningful difference between those two p-values, and there's nothing magical about a p-value of 0.05. In fact, in the example above, it is known that the binomial test is usually conservative, and the true level of significance, or your true alpha, is often less than 0.05 because it's a conservative test. However, the exactness of the test sometimes makes it preferable in practice. So it's really a shame that such an emphasis is put on p-values. And in practice, rather than just giving a p-value, always try to include a confidence interval in these scenarios to help the reader gauge the magnitude of the estimated effect along with the width of the confidence interval, rather than relying solely on p-values.